Space exploration has always faced a monumental challenge: maintaining equipment in inhospitable environments. Once launched into space, spacecraft are subject to extreme vibrations, drastic temperature variations, and the constant impact of micrometeorites and debris. To date, performing corrective maintenance in orbit is a virtually impossible or prohibitively expensive task, usually resulting in the premature loss of valuable assets. However, a promising innovation promises to change this scenario: the introduction of self-repairing composite materials, allowing the spacecraft's own structure to identify damage and heal it without the need for external human or robotic intervention. This cutting-edge technology is based on the development of smart materials that go beyond simple metal alloys or traditional composites. The focus is on creating advanced carbon fibers that incorporate internal healing agents. The basic premise is to transform the hulls and structural components of spacecraft into organisms capable of monitoring their own physical health. By making materials reactive and intelligent, a new era in aerospace engineering is opening up, where vehicle durability ceases to be a purely passive factor and becomes a dynamic and controllable characteristic throughout the mission's lifespan. To transform this vision into reality, a major European consortium was formed, drawing on the expertise of the Swiss companies Compair and CSEM, and the Belgian company Carmen Sens, under the sponsorship of the European Space Agency, ESA. This collaborative effort was named Project Cassandra, an ingenious acronym derived from the English Composite Autonomous Sensing and Repair of Composite Materials. This project is not just academic research, but a pragmatic effort to enable space infrastructures capable of remaining operationally viable for much longer periods than current technologies allow. The differentiating factor of Project Cassandra lies in the technology dubbed HealTech, developed by Compair. Traditionally, composites are valued for being lightweight and robust, combining polymers with fibers to withstand severe mechanical stresses. However, their main weakness has always been their susceptibility to delamination and microcracks resulting from thermal or mechanical shocks. HealTech reverses this vulnerability by integrating a latent curing agent within the composite matrix. When the material suffers a microcrack, the curing agent is there, waiting only for an external stimulus to flow and seal the gap, restoring structural integrity almost to its original state. The activation of this self-healing process is done through an ingeniously simple approach: controlled heating. To facilitate this process without relying on heavy external machinery, the design incorporates 3D printed aluminum grids directly within the carbon structure. When sensors identify damage, an electric current is sent through these grids, raising the temperature of the affected region to a level between 100 degrees Celsius and 140 degrees Celsius. This specific heat is the chemical trigger that causes the curing agent to become fluid, spread through the crack, and after cooling, solidify again, closing the structural defect. The system's intelligence is complemented by a network of fiber optic sensors, which acts as the spacecraft's nervous system. These fibers are embedded in the material's composition during manufacturing. They allow for real-time, continuous monitoring of variations in stress and material integrity. Unlike conventional inspection methods that would require complex external sensors, this full integration allows the spacecraft to detect a crack the moment it occurs, even if it is microscopic, initiating the healing process before the failure becomes critical. The experimental phase of this project has already yielded robust results. Researchers subjected samples to rigorous conditions mimicking the real space environment, including dynamic impact tests and extreme cryogenic stress, typical of liquid propellant tanks. The results were encouraging. The technology not only detected flaws with surgical precision, but also demonstrated uniform heating and a remarkable recovery of mechanical strength after repair cycles. This proves that the solution is physically feasible and can be implemented in structural components under load. With the success of the laboratory proof-of-concept tests, the next ambitious step of Project Cassandra is to transition from small-scale testing to application in complex components, such as fuel tanks. These are vital elements of any launch vehicle, and their structural integrity is paramount. By applying this technology to reusable fuel tanks, ESA is not only creating safer spacecraft but also boosting the European space economy, as components with extended lifespans drastically reduce the need for constant manufacturing and replacement of parts. Ultimately, this innovation represents a fundamental step towards sustainability in space exploration. By extending the lifespan of spacecraft and ensuring their reuse, the project reduces both waste and operational mission costs, indirectly combating the accumulation of space debris. The integration of intelligent sensing with self-repair capability is therefore the future of orbital infrastructure, paving the way for longer, more frequent, and economically viable missions for the next generation of human and robotic exploration in space.